Welcome to another CHEM271 tutorial session. This one will be looking at glycogen metabolism. However, we will only be looking at the regulation of glycogen metabolism. We will not be looking at any of the reactions. So we're just going to be looking at the part that I think is the most complex, which is the regulation. So let's first look at glycogen degradation and how that's regulated. So glycogen degradation is regulated at the enzyme glycogen phosphorylase. Okay, so what is glycogen phosphorylase doing? It's taking glycogen, it is adding a phosphate to it, which is removing a single glucose from glycogen, so glycogen N+1 to glycogen N, and by phosphorylating a glucose, you get glucose 1-phosphate. Okay, and this is breaking the alpha 1,4 bond, not the alpha 1,6 bond. Okay, so that's just a brief summary of what this enzyme is doing. It is removing glucose from glycogen, which is a lot of glucose sort of stuck together, right? Okay, so we know that the regulation happens at glycogen phosphorylase. So let's start over here. When glycogen phosphorylase is not phosphorylated, so it just has this sort of OH group here, right? So no phosphate on glycogen phosphorylase, just the OH. This is regulation by reversible phosphorylation. So when the enzyme glycogen phosphorylase is not phosphorylated, when it has an OH, it is inactive. However, when it has this phosphate group on it, this activates, okay? So phosphate group, active, no phosphate group, just an OH, inactive, okay? That's important to know. So in order to activate and phosphorylate glycogen phosphorylase, the enzyme, right? This is a regulation happening by phosphorylating the enzyme itself. The enzyme that phosphorylates the enzyme is phosphorylase kinase. So this is going to be using ATP in order to phosphorylate glycogen phosphorylase and activate it, okay? Now to inactivate glycogen phosphorylase, this is being done by a phosphatase. This is being done by protein phosphatase 1. So protein phosphatase 1 will use water. This is a hydrolysis reaction to remove the phosphate group from glycogen phosphorylase and inactivate it. So, okay, so it's under regulation by reversible phosphorylation. However, it is also under regulation by allosteric regulation, by binding of allosteric regulators, okay? So this is different between the skeletal muscle and the liver. So let's first look at in the skeletal muscle. So in the skeletal muscle, it is the dephosphorylated form of glycogen phosphorylase that is the sort of point of allosteric regulation. So it will be the inactive dephosphorylated form of glycogen phosphorylase that will be regulated allosterically in the skeletal muscle. So what is happening here? So essentially through allosteric regulation, high levels of AMP will activate it. So notice how it's not phosphorylating it. It's still dephosphorylated, but now it is active because an allosteric regulator, AMP, has binded to it. Okay? And when ATP or glucose 6-phosphate bind, that will inactivate it. Okay? So no change in phosphorylation state, just the binding of allosteric regulators is enough to activate or inactivate, okay? So let's try to make sense of this. So high AMP, what does that indicate? That indicates low energy charge. So if there's low amounts of energy in the cell wants to degrade glycogen, make glucose so that glycolysis can happen. And glycolysis, citric acid cycle, etc., those will be used to make ATP. So high AMP indicates low ATP, low energy. The cell wants to make energy by degrading glycogen. On the opposite end, though, if we have a lot of ATP and a lot of glucose 6-phosphate, which glucose 6-phosphate is sort of a stand-in for the glucose concentration. So we have a lot of ATP, we have a lot of glucose. This indicates high energy charge. So the cell has a lot of energy. It does not need to make more energy. It does not need to do more glycolysis. So if it's not needing to make energy, instead it will inactivate glycogen phosphorylase, inactivate glycogen degradation. There's no need to make more glucose to have more glycolysis. You want to sort of shut down glycolysis because you don't need more energy. Instead, if you have a lot of glucose hanging around, maybe you want to store it instead and do glycogen synthesis, but we'll look at that in a bit. Okay, so that is happening in the skeletal muscle. Remember the skeletal muscle cells? They're just storing glucose as glycogen for themselves. So this is just for their own energy usage. Thus, they want to respond rapidly to levels of ATP and of levels of glucose. Okay, so that way they can sort of know when the muscle needs more energy in order to continue contracting. Okay, so now in the liver, the point of allosteric regulation is at the phosphorylated form of glycogen phosphorylase, so the active form, and then through the binding of glucose at high glucose concentrations, this will allosterically inactivate glycogen phosphorylase while it is still in the phosphorylated form in the liver. So high glucose inactivates it. So what this means is that if there's already a lot of glucose, the cell does not need to make more, right? If there's a lot of glucose, it does not need to degrade glycogen. It does not need to make more. It doesn't need to feed into glycolysis, okay? So the reason why the liver would want to regulate glycogen metabolism is because the liver is the site of gluconeogenesis. So the liver is essentially storing glycogen so that if it makes ATP for the brain. So if the brain needs ATP, it will degrade glycogen to make ATP to give to the brain, okay? So that's why it is under this. High glucose in this case indicates high levels of gluconeogenesis. Thus, you do not want gluconeogenesis to be running at the same time as glycogen degradation. You don't want to produce glucose from these two sources. Instead, if you have a lot of glucose being made from gluconeogenesis, you'd rather store that and make glycogen, okay? So that is glycogen degradation. Let's look at glycogen synthesis now. All right, let's now look at the regulation of glycogen synthesis. So this occurs at the enzyme glycogen synthase. So what is this enzyme doing? It is taking a UDP glucose and adding it onto a glycogen to make a glycogen N+1, and then getting rid of the UDP, okay? So this is making alpha-1,4 bonds. Within glycogen, it is building up glycogen. It is adding a glucose to glycogen, okay? So this enzyme is our major point of regulation. It again undergoes reversible phosphorylation, but it additionally undergoes a bit of allosteric regulation in the liver, much like what we saw with glycogen phosphorylase, okay? So let's first look at this. So glycogen synthase is inactive when it is phosphorylated, okay? So remember how glycogen phosphorylase was active when it was phosphorylated? Glycogen synthase is inactive when it's phosphorylated. So glycogen synthase is the opposite of what we see with glycogen phosphorylase. Also, glycogen synthase, when it is dephosphorylated, is active, okay? So in order to activate glycogen synthase, a hydrolysis reaction removes the phosphate. This is done by protein phosphatase 1. You might recognize that from glycogen degradation. It's the same enzyme. So protein phosphatase 1 is going to activate glycogen synthase by dephosphorylating it, but it's also going to inactivate glycogen phosphorylase also by dephosphorylating it. So protein phosphatase 1, this is going to activate synthesis, but inactivate degradation. Is that readable? Yeah. Okay. So, and then in order to inactivate glycogen synthase, protein kinase A will come in and use ATP to phosphorylate it. This is a different kinase right? In degradation, it's phosphorylase kinase. In synthesis, it is protein kinase A, okay? Now let's look at what happens in the liver. So this is allosteric regulation of the phosphorylated form of glycogen synthase. So the phosphorylated form, glucose 6P can bind to it allosterically at high concentrations and activate glycogen synthase. So what does high glucose 6P represent? It just means that there's a lot of glucose in the cell, in the liver, and this allows the liver to immediately sort of respond to that high glucose concentration and start making glycogen. So allosteric regulation is a little bit faster than reversible phosphorylation, which requires some hormonal regulation. So this allows the liver to rapidly respond to glucose concentration. So liver can rapidly respond to high glucose and thus synthesize glycogen, okay? So there are two levels of regulation to activate glycogen synthase, right, in the liver: allosteric from high glucose concentrations and also dephosphorylation, okay? So that is glycogen synthesis. Now let's sort of look at the total trends going on here in glycogen metabolism and a bit more into hormonal regulation. All right, let's finish our discussion of glycogen metabolism regulation. So let's first look at the major trends in glycogen metabolism regulation. So overall, phosphorylation of both glycogen phosphorylase and glycogen synthase. So together, what this does is it promotes glycogen degradation and inhibits glycogen synthesis. So remember, phosphorylation is going to activate glycogen phosphorylase and promote degradation, and it is going to inactivate glycogen synthase and inhibit synthesis. So phosphorylation pushes glycogen in the direction of degradation, while dephosphorylation is going to inhibit degradation. So dephosphorylation will inactivate glycogen phosphorylase, while dephosphorylation will also promote synthesis. So it will activate glycogen synthase, okay? So notice how one singular process will push the cell in one direction, okay? So it'll promote one and inhibit the other, while dephosphorylation promotes synthesis and inhibits degradation. So this sort of prevents both pathways from being active at the same time. Only one pathway will be activated at the same time, meaning this will prevent futile cycling of sort of both reactions happening at the same time in the same, which leads to no net degradation or synthesis of glycogen. Okay, so this is sort of the main takeaway. If you can remember this, you've remembered most of glycogen metabolism regulation. So the last bit to go over is hormonal regulation. So we have insulin, glucagon, and epinephrine. So let's first look at insulin. So insulin will promote storage and synthesis. So this will activate glycogen synthase, and it will prevent degradation, so inactivate glycogen phosphorylase. It does this through activating protein phosphatase 1. So this will promote dephosphorylation, which will inhibit degradation and promote synthesis. So it together will activate protein phosphatase 1. Remember, protein phosphatase 1 is shared between the regulation of degradation and of synthesis. So protein phosphatase 1 will inactivate glycogen phosphorylase, and it will activate glycogen synthase, okay? So what is the reason behind this? So insulin indicates high blood glucose. It indicates an organism is well fed. If you have a lot of blood glucose, you want to lower that. And one way to do that is by activating glycogen synthesis, activating the storage of glucose. So thus it will activate glycogen synthase and inactivate glycogen phosphorylase through the activation of protein phosphatase 1. Okay? Now, glucagon and epinephrine. So these will promote energy production. So energy production is promoted by glycogen degradation, the production of glucose. This glucose can then enter glycolysis and produce ATP. So if we want energy, we need to degrade glycogen, activate glycogen phosphorylase, and we also then want to prevent glycogen synthesis. Okay, if we have a lot of glucose, we don't need, or sorry, if we do not have a lot of glucose, we don't want to use the little glucose in the cell to make glycogen. We want to make ATP with that. Okay, so promote degradation, prevent synthesis. How does this work? So glucagon and epinephrine activate the production of CAMP. CAMP is cyclic AMP. This goes on to activate a bunch of kinases. This includes phosphorylase kinase and protein kinase A. So these are going to phosphorylate both glycogen phosphorylase and glycogen synthase. So through the phosphorylation of glycogen phosphorylase, we promote degradation, energy production, glucose, and then we inhibit synthesis, okay? CAMP will also inhibit protein phosphatase 1, so that will further lead to this trend of phosphorylation, preventing dephosphorylation, okay? So what is the reason behind this? So glucagon indicates low blood glucose levels. So if we have low blood glucose levels, we want to increase blood glucose levels by degrading glycogen. And then epinephrine, this is your stress hormone, your fight or flight hormone. Okay, so if you're stressed out, you need a lot of ATP to either fight or run away, flight. So epinephrine, it's going to promote ATP production, promote the degradation of glycogen, which leads to the production of glucose, activates glycolysis, makes ATP. You need this ATP in order to quickly move and get away from whatever stress is in the environment, okay? So that is regulation by different hormones, and that does it for glycogen metabolism. Next time, we will look at the citric acid cycle. Thank you.